Welcome back to Practical PyTorch. In this video you'll learn how Autograd works, how the forward pass records a computation graph, how dot backward plays it in reverse, and how every weight gets its gradient without you ever doing calculus by hand. This line builds a prediction, y equals w times x plus b. This line measures how wrong it is. Loss equals y minus t squared. Training needs the derivative of that loss for every weight, and real networks have millions of weights. Nobody works those out on paper. So PyTorch does it for you. When a tensor tracks gradients, PyTorch records the steps you run on it, then plays the record backward to hand you the derivatives. That recording is Autograd. This video has 4 parts. First, requires grad equals true turns the recording on. Second, the forward pass builds a graph with a value in every node. Third, dot backward walks that graph in reverse, multiplying along the path. And fourth, the leaves get a dot grad, while torch dot no grad lets you opt out. First, the forward pass. Let's build the graph one line at a time and watch PyTorch write it down. We make w equal to 3 with requires grad equals true. That flag tells PyTorch to start watching this tensor. X is 2 with no flag. It's just data, so it needs no gradient. B is 1, and it gets requires grad equals true as well. It's another value we want to learn. And t is 10, the target. It's data too, so no gradient. So the split is simple. W and B are what we want to learn, so they need a gradient. X and t are given data. The leaves are the inputs you make directly, where the graph starts. This is W equal to 3, a leaf that needs a gradient. This is X equal to 2. It's data, so it carries no gradient. And this is B equal to 1, another leaf that needs a gradient. A leaf is a tensor you made directly, the one you typed, not one PyTorch computed. The gradients will land in the leaves that need 1, W, and B. Now we run y equals w times x plus b. PyTorch computes the value. 3 times 2 plus 1 is 7. As the line runs, PyTorch draws an edge from W into Y, recording that W helped make it. It draws another edge from X into Y, the same way. And a third edge from B into Y, so Y is not a leaf. PyTorch computed it from the 3 inputs. The number and the graph appear together. Running the line both gives you 7 and writes down how it got there. Now the target arrives. T equals 10 is the number the model should have produced. It's data, so it needs no gradient. It sits ready on the right, and the next line uses it. The last line is loss equals y minus t squared. PyTorch computes it. 7 minus 10 is minus 3, and minus 3 squared is 9. It draws an edge from y into the loss, and an edge from t into the loss. The graph is now complete. Leaves on the left, the loss on the right, and every step in between is on record. Now that the graph is built, let's print y and see what it carries. And print the loss the same way. Y prints as tensor 7 with grad fn add backward, and loss prints as tensor 9 with grad fn pow backward. That grad f, n is the recording printed. It's the proof. Y remembers it came from an add, and loss remembers it came from a power. A leaf like W has no grad fn because nothing computed it. That's the whole forward pass recorded. Now we play the recording backward. We call loss dot backward, and the walk begins here at the loss on the right. It takes the first edge back, from the loss to y. On that edge it computes the gradient reaching y, 2 times y minus t, that is minus 6. Notice one thing here, y is not a leaf. The gradient passes through it, but its dot grad stays empty. We'll come back to that. The walk takes the next edge back, from y to w. The local slope on this edge is x, which is 2. So we multiply along the path, minus 6 times 2. That's minus 12, and it lands in w dot grad. W is a leaf, so the product is stored. This is the chain rule in one move. The gradient reaching y times the local gradient of the edge. Same walk, another edge, this time from y to b. The local slope here is 1, so minus 6 times 1. That's minus 6 stored in b dot grad. B is a leaf too, so it keeps its gradient. Nothing new in the method. The gradient reaching y times this edge one more time. What about x? Its edge does have a local slope, the slope of y with respect to x, which is 3. But that chip is gray for a reason. X was made with no gradient. So Autograd stores nothing for it. X dot grad stays none. Autograd just skips it. The slope is real math, but it stays gray. Autograd never uses this edge because x is only data. So x dot grad is none. The whole walk was one call, loss dot backward. Now weed the leaves, print w dot grad, and print b dot grad. W dot grad is tensor minus 12, and b dot grad is tensor minus 6, exactly the two numbers off the figure. One dot backward call walked the whole graph and filled both leaves at once. Let's name what just happened. The gradient into y is minus 6. On the way to w, multiply by 2. Minus 6 times 2 is minus 12. On the way to b, multiply by 1. Minus 6 times 1 is minus 6. That's the chain rule, the same rule from calculus. Multiply the slopes along the path. The backward walk is just the chain rule, run for you. So the leaves have their gradients, but what about the tensors in the middle? Let's ask for x dot grad. We already know x never requested a gradient. And y dot grad. Y is plainly in the graph, so surely it has 1. Both print none. Two different reasons though. X never asked for a gradient and y is not a leaf. PyTorch even warns you on y dot grad. The dot grad of a tensor that is not a leaf is being accessed. Dot backward fills the leaves only. The walk went through y. It did not stop there. One last piece. Recording the graph is something you can turn off. Sometimes you want the math but no graph. You wrap the code in with torch.noGrad. Inside it, we compute z equals w times x plus b, the same arithmetic as before. But this time z has no grad fin, the line was not recorded at all. Inside torch.noGrad, PyTorch does the arithmetic but records nothing. No graph, no backward, less memory. You use it every time you just want the answer, like checking a trained model. Let's bring it together. Requires grad equals true turns the recording on. The forward pass builds a graph, and dot backward walks it in reverse. Each edge multiplies, and the products land in the leaves dot grad. And torch.noGrad turns the recording off. You never differentiated anything by hand. The graph and one dot backward did it all. Quick check before we go. After loss dot backward, what does the intermediate tensors y.grad hold? Pause and predict. The full reasoning is in the course answers file, but remember, only leaves get a .grad. You can now get the gradient for every parameter, but the whole backward walk started from one number, the loss. Dot backward needs a single number to begin from, and that number is the loss. Choosing it is choosing what the model learns. That's the next video. See you there.